All right, so let's finish up this. So first of all, metallic and ionic bonds, these are not molecular. And the highlighted words are the ones you need to fill in your notes. But basically, that metallic and ionic bonding forces that hold individual units together are the forces between the units uh, are the same. The pure metal substances have metal atoms held together by delocalized electrons that bounce around between the atoms, while ionic compounds are held together by that alternating positive and negative charge, and they form a crystal lattice. So these are very strong forces. They're not molecular in nature, and they result in solid things. And the only exception is mercury is a metal. So metallic bonding, and here's a visual of it. You have these ions, these metal ions, and the electrons, the valence electrons, will sort of swim around among them. And it's sort of like if you bring a floaty to a giant pool situation like this. If every person brings a floaty, sometimes you might be someone without a floaty, like this guy here. And sometimes you might have two floaties, like this person here. But this person might get bored of that, and it'll just sort of find its way. And so as long as everyone brought something, everyone has one nearby. And that's sort of what happens here with these electrons in the metal bonding situation. All right. Intermolecular forces and states of matter. This is important. So different states of matter, solid, liquid, gas, are caused by the forces that hold the molecules together. The greater the bonding forces, then the particles are more attracted and they're more likely to be solids. The weaker the bonding forces, the particles and molecules aren't as attracted and they're more likely to be a gas or a liquid. So just to be clear, the intramolecular force is the bond, the covalent bond, the sharing of electrons. That is a very strong bond. That is usually not going anywhere without a chemical reaction. What we're talking about here are the intermolecular forces, and those are weak, and those are the forces between one molecule and another. So they're not shared electrons. They're just, why would these two things interact and not want to get away from each other when you melt them or boil them? And it turns out the strongest of these is called a hydrogen bond. Now, a hydrogen bond is unique in that it needs a hydrogen. And that hydrogen needs to be bonded to either an oxygen, a nitrogen, or a fluorine. And as a result of the electronegativity difference, that's a very polar bond wherein hydrogen is not really getting much electron at all. Oxygen is getting a lot of electron. This has a much higher electronegativity. And because it has all that electronegativity and that electron density, it becomes a little more negative. It's not a full negative charge. It's not like a -1 extra, but it's a little bit more negative. And the hydrogen becomes a little bit positive. That electron is floating in here mostly on the oxygen side of things. And since hydrogen is just a proton otherwise, that's sort of an exposed positive end here. And that positive end will now be attracted to the negative oxygen of another water molecule and so forth. So there's an attraction between this plus minus. And as a result, we get what's called a hydrogen bond. It's not really a bond, but just sort of an attractive force between the hydrogen of one molecule and the oxygen or fluorine or nitrogen of another molecule. And here's sort of a visual of how this is in nature. Typically, as something gets heavier, carbon going to silicon, going to germanium, whatever that is, going up to tin, these are getting heavier as you go up, and the boiling point will increase because of that heaviness. It's harder to get this moving around than a CH4. You would expect to see that same trend here and here and here with groups 17, 16, and 15. And you do see as something gets heavier, the boiling point goes up. There are these huge exceptions, though, and these are the hydrogen bonding triumvirate. And that's oxygen, fluorine, and nitrogen, because when the hydrogen is bonded to these things, they tend to have this sort of hydrogen bond situation and will stick molecule a little more, and their boiling points therefore are higher than would be expected. All right, so there's dipole forces. These are forces between polar molecules. So if you think of what we were just talking about with electronegativities, there's a bond in a molecule. It's not being shared equally. The electrons will favor one over the other. So here's a chlorine bonded to an iodine, and the chlorine gets a little bit more negative because it's getting more custody of those electrons. The iodine, because it's not has as much custody, gets a little bit positive. And now this slight, and that's what that little delta means, this slight positive negative is spreading throughout the other molecules. And because of that, now this chlorine, which is a little bit negative, is attracted to an iodine, which is a little bit positive. So this is an intermolecular force, this negative positive-ish attraction. It's not near as strong as this bond. It's not near as strong as an ionic bond, but it's a slight attraction that will make these things want to stay closer together, and it'll make it harder for them to move away from each other. Same is true here with acetone. The carbon-oxygen bond is a very polar bond, and such that the oxygen gets much more of the electron density. It becomes a little bit negative because of that, and the carbon becomes a little bit positive. So the oxygen of another molecule can now be attracted to this carbon by this plus minus difference here. And same thing here. So that's dipole-dipole. And now London dispersion, one of my least favorite of the, or van der Waals forces. I'm not sure how solid this is, but basically what it says is when two molecules, or in this case, two neon atoms, kind of float near each other, the electrons of one have this repulsion effect of the electrons of the other, and it kind of pushes those electrons to one side. And then it becomes sort of a cascading effect where the electrons are now attracted to the nucleus and all this. Anyway, my point is this is a lot of hand waving. There's a lot of like, hey, that happened, right? So it's very weak force. It's present in all molecules. It's called a van der Waals force or a London dispersion force. That's the logic of it. I'm not a huge fan of this one. But anyway, the point of all this is that ionic and metallic bonding is very strong. That does not happen in molecules. It happens with ionic compounds or metals. And when we talk about intermolecular forces, forces between molecules, forces between things that are covalently bonded, that's where you will see hydrogen bonding, where you'll see dipole-dipole, and where you'll see London dispersion. And just to give you an idea, this is like welding. Ionic, metallic, that's like welding things together. That's a pretty strong bond. Hydrogen bonding is not that strong. It's kind of like using crazy glue. Dipole-dipole is kind of like using glue stick, and London dispersion is kind of like using the sticky note glue to hold things together. So they're not near as strong as ionic, but they exist, and hydrogen being the strongest. So all molecules, if we ever ask you this on a quiz or a test, if it's a molecule, if it's a covalently bonded situation, they all have London dispersion, that hand waving one. If the molecule has a polar bond, now it's a good candidate to have a dipole-dipole interaction. And if a molecule has a hydrogen bonded directly to a fluorine, oxygen, or nitrogen, now it is a hydrogen bonding candidate. And that's how we would ask that. So that is the unit. And we can discuss this more as you wish.